Welcome to The Explainer. Today, we're decoding the fundamental split in supervised machine learning by looking directly under the hood of how AI learns. Look, if you've ever wondered how the code powering everything from stock market bots to self-driving cars actually functions, you are absolutely in the right place. We're going to strip away the intimidating jargon and break this down as if you're learning it for the very first time. So let's kick things off with a massive question. How do these algorithms actually translate real life into math? I mean, how does an artificial intelligence view our totally messy, unpredictable physical world? Well, it turns out AI generally approaches reality using one of two entirely different philosophies. And here's the kicker. Choosing the wrong one will completely break your system, wasting your time, your money, and some serious computing power. All right, here's our agenda for today. 1, the two camps of AI. 2, measuring success and error. 3, hardware and GPU constraints. 4, agents working as a team. And 5, choosing the right algorithm. Let's get into it. Section 1, the two camps of AI, decoding discrete buckets versus continuous infinite scales. Let's start with the big picture, okay? The entire field of supervised machine learning basically splits based on the final outcome the model is looking for. You're either drawing boundaries to put things into distinct buckets, which represent specific categories, or you're finding a single point on a continuous, infinite scale to predict a mathematical quantity. As you can see here, on the left, we've got our buckets for distinct categories, and on the right are infinite scales for continuous values.
Let's ground this with a real-world scenario. Imagine you're a real estate agent trying to navigate today's crazy housing market. You're feeding data points, like square footage, the number of bedrooms, neighborhood zip codes, into an AI model. Your ultimate goal here is to find an exact market price for a branding listing.
The AI crunches the numbers and spits out a fluid value, like $500,000. This is the perfect example of regression. Why? Because the output is continuous and mathematical. The answer isn't a named category, it's a sheer value. And because it sits on a truly infinite scale, the output literally could have been $499,999 or $500,001. Regression is the language of physics, finance, and pure measurement.
Now let's contrast that with something you deal with every single day, your email inbox. Your email provider analyzes the text of incoming messages, the sender addresses, the frequency of sketchy links, all to keep your primary feed perfectly clean. But here's the thing. An email cannot be 40% spam in its final destination, right? It's a hard binary choice. It either goes to your inbox or it goes straight to the junk folder. This discrete boundary drawing is called classification. It answers what kind of thing this is, not how much. And that's a crucial distinction for keeping your digital life organized.
Section 2, measuring success and error, the mathematical intuition and loss functions. Now, to understand why these models run so differently on a microchip, we need to go a bit deeper into how they measure their own mistakes during the training phase. I mean, how does an AI even know it did a good job? Well, every AI has a brain for its learning process called a loss function. Think of it as the mathematical penalty a model pays for being wrong. The model's entire goal in life is to get this penalty score as close to 0 as possible. And this penalty? It's calculated fundamentally differently for our two camps. In regression, physical distance really matters. If the actual house price is $500,000 and your model predicts $450,000, that massive physical distance of 50 grand is heavily penalized using something called mean squared error. By literally squaring the error, the AI exponentially punishes itself for massive outliers, which forcefully drags the line of best fit closer and closer to the actual data. But in classification, physical distance doesn't mean a thing. If a model is 99% confident an email is not spam when it actually is a phishing scam, cross-entropy loss hits it with a massive penalty for being confidently wrong. Cross-entropy doesn't care about distance at all. It purely penalizes unwarranted arrogance when assigning a label. And because of these mathematical differences, they learn in totally different environments. Regression usually enjoys a smooth, convex path to the right answer. Picture a marble rolling down into a perfectly smooth bowl. It easily finds the bottom, right? But because classification forces hard boundaries, deep classification models face jagged, non-convex landscapes where they can easily get stuck in suboptimal little valleys. This is exactly why classification often requires complex momentum algorithms just to keep the learning process moving forward. Section 3, hardware and GPU constraints, how the math dictates microchip performance. Okay, this is where it gets really cool.
These mathematical differences physically bottleneck high-performance GPU hardware. This isn't just theory, it directly changes how memory is consumed on your actual microchips. Regression is incredibly fast because it relies on simple subtraction and multiplication for a single output neuron. Classification, however, requires a hardware-heavy operation called the softmax function to calculate exponentials for every single possible category. When you use batch processing to push massive amounts of data through the GPU at once, how that data is mapped in the GPU's memory layout becomes absolutely critical. Those massive softmax summations will aggressively devour your memory bandwidth limits. To put that hardware overhead into perspective, imagine the number 50,000. If you're running a large language model classification task, like predicting the next word in a sentence, and you have a vocabulary output of 50,000 token classes, that softmax calculation becomes your primary hardware bottleneck. Your GPU has to compute exponentials for all 50,000 potential words simultaneously for every single step. So while increasing your batch size might seem like a great way to improve throughput, that math makes your memory consumption totally skyrocket. Section 4. Agents, working as a team, blending models for robotic execution. Let's zoom back out for a second. In the real world of agentic AI, advanced systems rarely just use one or the other. They work together as a highly coordinated team. Think about a continuous decision loop in a robot. The agent first uses classification as the perception model to identify its environment. It looks at a camera feed and asks, okay, is this an obstacle or an open path? Once it categorizes the environment, it hands the decision off to regression, the executor, to apply precise physical movement. The regression model calculates, to avoid this, apply exactly 4.5 newtons of torque to the steering motor. One model names the world and the other measures it. Section 5. Choosing the right algorithm, your step-by-step decision framework. So, knowing when to use which approach is absolutely crucial. When you're approaching a new AI problem, just run your target through this simple step-by-step guide. Step 1, ask, is the output ordered and mathematical? If yes, it's regression. Step 2, is the output a label or a name? If yes, classification. Step 3, are you ultimately making a yes or no decision? Even if probability is involved, a final yes/no means you are drawing a hard boundary, which, you guessed it, is classification. Seriously, keep this table handy for your own projects. If you want to know how much, like a stock market price or age estimation, choose regression. But if you need to know what kind, like malware detection or identifying the emotion in sentiment analysis, you must use classification. Using the wrong algorithm is literally like trying to measure the temperature with a ruler. It just fundamentally does not compute. As we look toward the future of self-driving cars, agentic bots, and advanced robotics, these lines are going to continue to blur into incredibly complex hybrid systems. As our machines become more and more autonomous, how will the next generation of AI perfectly balance the measurement of our physical world with the logic of identifying it? Mastery of machine learning ultimately comes down to knowing exactly when to do which. So, what will you build next?